In this video, I'm going to go over some different integrals that involve rational functions. And the trick to these is identifying what type of rational function, what strategy we're going to have to deal with. So that could be, it's a natural log. It could be an inverse trig function. We could have to use long division. Completing the square is sometimes a strategy. So I'm going to best help to identify when you're looking at something, which of those strategies to look at. So first, just integral of 1 over x. That is the natural log of x. We put absolute values around it because the domain of this includes negative values, but we can't take the negative of a log. And so we want the integral for all of these, so we do the absolute value to deal with this. This is going to be the same as 1/4 times the integral of dx over x. So that's just going to be 1/4 natural log absolute value of x. If there's no constants or anything here, then we can just say this is the natural log of x plus 2, where we have to be careful, and we're going to see this in a couple examples, is if there is a constant, then we got to deal with that. Now it's important. Natural log is only if the denominator is a degree 1. If it's any other degree, then we're looking at potentially a power rule. So this would be the same, it would be similar to 1 over x squared, except for it's 1 over x plus 2 squared. We know the derivative of 1 over x is negative 1 over x squared. So this integral is going to be negative 1 over x plus 2 plus c. If you don't recognize that right away, that's okay, because you could rewrite this whole thing as x plus 2 to the negative 2, and then just apply our power rule. This one here does have a coefficient. So strategy number 1 would just to be to kind of do it. I'm going to go ahead and use a u substitution, though. You can get there without it, but I think u substitutions are super handy in order to do these integrals and deal with these constants. So if my u is 3x plus 2, my du is going to be 3 dx. We don't have a 3 dx, but we can make a 3 dx as long as I undo that fact. So my 1/3 goes along for the ride. 3 dx becomes my du, and 3x plus 2 is my u. And we're right back to natural log. So this will be 1/3 times the natural log of u plus c. And then we'll go ahead and substitute back in our u. Okay, here, at first glance, it looks complicated, but we notice I've got x to the 5th here, and the derivative of x to the 5th is 5x to the 4th. So this is just ripe for a u substitution. Okay, so my 5x to the 4th becomes du. My x to the 5th plus 1 becomes u, and we have another natural log. All right, so the topic of this lesson was limits involving rational functions. Well, I don't have a rational function here. I have tangent. That's a trig function. But I can rewrite it as a fraction. So this is going to be sine of x over cosine of x. And suddenly we can integrate this using a u substitution. So I'm going to let u equal that denominator, which is cosine, which means du is a negative sine of x dx. So I'll sneak a negative in there so I can replace that with the du, but I'm going to undo that here. And just like that, we're back to natural log. Okay. So not one that you need to know for the AP exam unless you are clever and do this rational, splitting it up into sine over cosine. But the integral of tangent is actually negative ln cosine of x. So let's look at cotangent. Using our trig identities, cotangent is equal to cosine over sine. So similar to what we did here, I'm going to let my u equal the denominator, which in this case is sine. So my du is cosine of x, which I have, no adjustments needed. Okay, and we get natural log absolute value of u plus c, which is going to be natural log absolute value of sine of x plus c. Now these really aren't rational functions. They're functions that have fractions. So I kind of grouped them all together. But these ones are ones that just aren't always so obvious. But we have 1 over the square root of 1 minus x squared. That is the derivative of sine inverse of x or arc sine x. You'll see those interchangeably. This one is sort of like that. So I'm going to do some manipulation on this first, because we really need the 1 minus x squared, and I have an x squared but not a 1 here. So the first thing I'm going to do is pull out a 25, which will leave me with a 1 minus x squared over 25. Okay, square root of 25 is going to be 5. And then I'm going to rewrite this x squared over 25 as x over 5 squared. Okay, then I can do a u substitution. I'm going to let u equal that x over 5, which means du is 1/5 dx. So that's going to become u. This 1 over 5 is going to become du. I'll go over here. Okay, and just like that, we have sine inverse. So this is going to be the sine inverse of u. And then we'll go ahead and substitute back in. Okay, this one is a rational function, but we have 1 plus x squared, or 1 over 1 plus x squared, which is the derivative of tangent inverse. Okay, this one's close to that, but that 16 is kind of messing us up. So I'm going to factor that out like I did last time. Okay, which means the x is now x squared over 16, and my 16 becomes a 1. Then I'm going to rewrite that is x over 4 squared. Okay, so I'm going to let u equal x over 4, which means du is 1/4 dx, which I kind of have that. I have a 1/16, so I can split that up into a 1/4 times a 1/4. So if I do that, I'm going to be left with a du, there'll be a 4th left there, and then u squared plus 1. So this will be 1/4 tangent inverse of u, and then I can substitute back in. Okay, the next case we're going to look at is if there's no trig inverses that we can use, there's no natural logs, there's no convenient u substitution to get us something that we can integrate, like these. You know, if this was an x squared, then sure, we could do a u substitution, but it's not. If the degree of the numerator is bigger than or equal to the degree of the denominator, One strategy we can use is long division. We can break the function down into pieces that we can then integrate. So polynomial long division, we're literally going to divide x by x plus 1. So in long division, you look at what would I multiply this by to get this, and that would be a 1. Then we multiply down, and we subtract. X minus x is 0. 0 minus 1 is a negative 1. What would you multiply x by to get negative 1? Well, that's not going to happen. So we're going to have a remainder of minus 1 over x plus 1. We've done no calculus. We've just done algebra. But what we've created here is this is equivalent to this, and this I can easily integrate. Okay, so if I integrate 1, that's just going to be x. If I integrate that, that's a natural log. And we get our integral. Okay, here, degree is bigger on the top than the bottom. A u substitution isn't going to fix it, so we're going to use long division. All right, so what we'd multiply x by to get x squared is an x. So x times x is x squared. X times 1 is x. Then we subtract. So x squared minus x squared is 0. 0 minus x is going to give me a negative x. What would we multiply x by to get a negative x? Would be a negative 1. Multiply that down. All right, a negative x minus a negative x is 0. That's the good news. 0 minus negative 1 is 1. I can't multiply x by something to get 1 without it being a rational function. So my remainder is 1 over x plus 1. And that's our new form of the integral. Okay, the whole point of that algebra is just to break it down into something we can integrate. So we get 1/2 x squared minus x, and then another natural log. Okay, 15 is going to be similar, but we've thrown some more constants in there, so just more to keep track of. Okay, so what we'd multiply 2x by to get 12x squared would be a 6x. 6x times 2x is 12x squared. 6x times 1 is 6x. Okay, 12x squared minus 12x squared is 0. And we get a minus 6x. We'd multiply that by a negative 3. So 0 minus negative 3 is a positive 3, and that gives us our remainder. All right, so we'll rewrite our integral using our new format here. So integral, let me go down here to see we have enough room. Integral of 6x is going to be 3x squared. Integral of negative 3 is minus 3x. Here, I'm going to have a 3. This is going to be a natural log, but there's a coefficient here, so I need to undo that coefficient. Okay, because when I take the derivative of this, it had 1 over this times 2, so we undo that. Or do a u substitution. I didn't want to overcomplicate it with too many strategies in this one problem, but you absolutely can use more than one strategy per problem. When I originally wrote this, I put this on here to use long division, but then I looked at it and went, well, that's silly. We don't want to do long division. We're going to do a simpler version of division. Because I can break this up. If there's just a lone guy in the denominator, I can split this whole thing up. Okay, that's perfectly valid because I can combine these to get this. But by decomposing it like this, I get an x minus 1 over x. And each of those pieces is easy to integrate. So this is a good thing to recognize. Now, if you did long division, you'll get the same answer either way. It's just not really necessary in this case. So then we're going to integrate. Integral of x is 1/2 x squared. Another natural log. Hopefully we're starting to recognize those. This one's a definite integral. So we're going to have 1/2 e squared minus natural log of e minus 1/2 1 squared minus the natural log of 1. Natural log of e is 1 minus 1/2. Natural log of 1 is 0. So this just ends up being 1/2 e squared minus 3 halves. A next strategy that's not always obvious is to use completing this square. These are kind of contrived situations, if I'm being honest, but it is an AP strategy for specific rational functions. So I'm actually going to do this one. So for completing the square, we're going to be rewriting this. And just to help us out with our organization, I'm going to put a square. And I'm going to fill that in with a number here. But I don't want to actually change the problem. So if I'm going to add a number there, I need to subtract a number. Okay, now in completing the square, just like you did back in Algebra 2, the square is equal to b over 2 squared. What we're trying to do is this first half, I'm trying to make a perfect square trinomial. So the b in this case is 6. So if I do 6 divided by 2, I get 3. Squared is 9. So I'm going to add a 9 and subtract a 9. The key to this now is a perfect square trinomial. The two numbers that multiply to get a 9 and add to get a 6 are 3. So that's equal to x plus 3 squared. The rest of this, 10 minus 1, or 10 minus 9, is a 1. And if you take away the extra stuff, basically the 8 and this plus 3, we have a tangent inverse here. So this is going to be 8 times the tangent inverse. It's not x here, so this will be x plus 3 plus c. So that's where I say the kind of, because you kind of got to get to something that makes a tangent inverse, but that's how we do that. So that is different integrals with fractions, rational functions. Thank you for watching.